Capacitors store electrical energy in an electric field and are widely used in electronic circuits around the world. Practical applications include filtering noise in power supplies, smooth voltage fluctuations, and timing circuits. They work by having two conductive plates separated by an insulative plate called a dielectric. Once voltage is applied to these plates, an electric field develops in the dielectric. This energy is then dispelled from the capacitor, providing a power source to the circuit temporarily. The formula for calculating the capacitance, the amount of charge a capacitor can hold, is C equals charge over change in voltage. But in order to find the relationship between discharge time and resistance, a different formula must be utilized. The equation for calculating the theoretical discharge time is V equals VO times e to the power of negative t over RC, with V equaling final voltage, V0 equaling initial voltage, T equals time, R equals resistance, and C equals capacitance. If we manipulate this equation, we find negative RC natural log to the power of V over V0 equals T. This linearized equation will allow us to evaluate the accuracy of the experiment by allowing a comparison of the theoretical gradient and the experimental one. For this experiment, the materials needed are a 9-volt battery, breadboard, wires, resistors ranging between 1000 and 1 million ohms, and a capacitor 470 microfarads, and an oscilloscope. The experiment involves setting up a simple circuit with a push switch, a LED, a resistor, and a 9-volt battery. Once the capacitor is charged, the push switch will be turned off, and the time until the oscilloscope is reading a potential difference of less than 1 volt will be recorded. This will be done 3 times to ensure that the uncertainty of the experiment can be calculated. These are the results collected from the experiment. The methodology resulted in a highly precise data set with uncertainties ranging from 0.17 to 0.49%. The only exception being the data collected for the 1000 ohm resistor, likely due to the magnitude of the time values being very small, resulting in small uncertainties contributing to larger percentage uncertainties, but still within acceptable range. Figure 1 demonstrates the linearized data. It is evident that the experiment was a success as the methodology could produce results that are both accurate and precise. This is evident in the low error and uncertainty values in Table 1. This does not equate to the experiment being flawless. The small error was likely caused by uncertainty introduced from the devices used to record the data, such as the oscilloscope that has an uncertainty of plus minus 0.005. The linearized graph demonstrates the theoretical gradient of ln 1 over 9 is represented in the experimental data with an error of only 0.1649. To improve the experiment, it is recommended that higher precision measurements are taken of both the time and the resistance, as without verification it can prevent the data from reflecting the theoretical relationship.